Welcome back to the lab! Today we are diving hands-on into the Amazon Bedrock text and chat playgrounds to experiment with powerful generative AI models. As generative AI architects, we cannot rely on theory alone. We must experiment and iterate. Amazon Bedrock provides the ultimate laboratory for this exact purpose, the playground experience. The Bedrock Playground is a secure, no-code sandbox environment built directly into the AWS Management Console. Before you write a single line of Python code or deploy a complex API integration, the Playground allows you to interact directly with world-class foundation models from providers like Anthropic, Meta, and Cohere. Why is this sandbox so critical to your workflow? Because prompt engineering is an iterative science. The way a model responds to a specific instruction can vary wildly depending on its underlying architecture and training data. The Playground enables rapid, frictionless experimentation. You can type a prompt, evaluate the generated output, tweak your phrasing, and run it again in seconds. It completely democratizes AI access, allowing business analysts and developers alike to experience the cognitive power of these models instantly. Bedrock divides the sandbox into distinct workspaces tailored to specific modalities: the text playground, the chat playground, and the image playground. Today, we are focusing laser-tight on the text and chat interfaces. Let us dive in and explore how to orchestrate prompts within these dynamic environments to evaluate model behavior and perfect your generative AI interactions. This diagram maps the rapid prototyping workflow. The developer concept enters the Bedrock Playground, routes through either the text or chat interfaces, and loops continuously through rapid prompt iteration to achieve the perfect output.
Let us begin our deep dive with the text playground. While it may look simple, understanding its underlying mechanics is crucial for advanced generative AI development. The text playground provides a clean, open-ended workspace for evaluating generative text models. You provide a block of text, the prompt, and the model expands upon it, continuing the passage based on its training. But what makes the text playground distinct from a conversational interface? The critical difference is that the text playground is completely stateless. It does not inherently manage conversational context or remember previous interactions. When you click Run, the model looks at the text currently in the window, calculates the most probable sequence of tokens to follow it, and generates the output. Once the execution finishes, the transaction is over. It is a raw, powerful token continuation engine. Because of this stateless nature, the text playground is absolutely ideal for single-turn tasks. If you need to summarize a massive financial report, perform entity extraction on a medical document, or generate a block of SQL code, this is your go-to interface. It exposes the fundamental building blocks of generative AI, allowing you to focus entirely on the precision of your one-shot or few-shot prompts without the overhead of dialogue management. Let us look at how this stateless interaction translates to a Python API call. Let's analyze how the stateless text playground experience maps directly to this Python Boto 3 code. We initialize our Bedrock runtime client. Notice our prompt data string. It is a single direct instruction. Extract the key entities from this text. There is no conversational role assigned, no user assistant back and forth. It is purely a raw string input. Serious. We construct our JSON payload using the schema required by the Amazon Titan text model. We embed our raw string into the input text field and define our constraints in the text generation config. What happens during invoke model?
Now, let us pivot to an interface designed for dynamic, multi-turn interaction. The chat playground. While the text playground excels at single tasks, many enterprise applications, like virtual assistants or tutoring bots, require a conversational flow. How does the chat playground handle this? It introduces a structured format that explicitly defines roles, specifically the user and the assistant. When you use the chat playground, the interface is secretly maintaining a running transcript of the entire conversation. Each time you send a new message, it packages the entire history of the dialogue and sends it back to the model. This is how the model remembers what you discussed 5 minutes ago. It is constantly rereading the expanding context window. The chat playground allows you to test how well a model maintains character, recalls previous constraints, and handles nuanced follow-up questions. For models like Anthropic's Claude 3, this conversational structure is so fundamental that AWS requires a specific Messages API payload when interacting programmatically. Let us examine how to replicate this conversational role-playing in code. Let's decode the powerful Messages API structure used to programmatically replicate the chat playground. Unlike the raw string input of the Titan text model, here we construct a highly structured messages array. Look closely at the list of JSON objects. Each object explicitly declares a role. We start with the user asking a question. Then, crucially, we append a mock assistant role containing a previous answer. Finally, we add a new user role with a follow-up question. We are manually passing the conversation history back to the model. This is exactly what the Bedrock Chat Playground does behind the scenes. We package this array into our JSON payload, specify the required Anthropic version, set our token limit, and invoke the Claude 3 Sonnet model. By consuming this entire array, the model understands the context of the follow-up question and responds accurately. Mastering this array structure is the key to building intelligent, context-aware conversational bots. Observe the anatomy of conversational memory.
One of the most powerful and unique features embedded within the Amazon Bedrock Chat Playground is compare mode. When you are architecting a solution, choosing the right foundation model is your most critical decision. Different models have different reasoning capabilities, tonal variations, and pricing structures. How can you efficiently determine which model is optimal for your specific prompt? You use compare mode. By toggling a simple slider at the top right of the chat playground, you can configure the interface to run your prompt against up to 3 distinct foundation models simultaneously. It is absolutely brilliant. You can select an Anthropic Claude 3 model, an Amazon Titan model, and a Meta Llama 3 model, paste in a complex reasoning puzzle, and execute. Bedrock orchestrates the parallel invocations and displays the responses side by side on your screen. But compare mode is not just about reading the text output. It provides hard, quantitative metrics. Below each response, Bedrock displays the exact latency in milliseconds, the input token count, the output token count, and the associated cost for that specific invocation. This allows you to objectively evaluate the cost-quality-latency triangle. If a smaller, cheaper model provides a satisfactory answer 500 milliseconds faster than the heavy-duty model, compare mode gives you the exact data you need to make that architectural decision instantly. This illustrates the parallel processing power of compare mode. A single complex prompt passes through the router and is evaluated simultaneously across 3 models, returning side-by-side textual outputs paired with precise performance metrics. Serious. Whether you are using the text or chat interface, typing a prompt is only part of the equation. To truly engineer the output, you must manipulate the inference parameters. Foundation models are probabilistic engines. They predict the next word based on mathematical probabilities. By tuning specific parameters, we can control how the model samples these probabilities, directly altering the creativity and predictability of the response. Let us start with randomness. The most famous parameter is temperature. Temperature scales from 0 to 1. A low temperature, like 0.1, forces the model to pick the absolute most probable next word every single time. It is highly deterministic, perfect for analytical tasks or SQL generation. Amazed, but crank the temperature up to 0.9 and the model starts taking risks, selecting lower probability words, resulting in highly creative, diverse poetry or marketing copy. Next is top P, or nucleus sampling. Top P evaluates the cumulative probability of words. Setting it to 0.9 tells the model to only consider the subset of words that make up the top 90% of probable options, dynamically filtering out the absolute lowest probability gibberish. Finally, top K truncates the vocabulary list to a hard number.
If top K is 50, the model only ever looks at the top 50 most likely next words, regardless of their cumulative probability. Let us see how these dials are configured within an API request payload. Let's observe how we inject these tuning parameters into our application logic. In this Python snippet, we define an inference config dictionary to hold our dials. We set the temperature to 0.7. Because we are asking for a highly creative marketing slogan, we want a high temperature to encourage diverse, non-obvious vocabulary choices. However, we want to maintain coherence, so we engage top P and top K. By setting top P to 0.9, we instruct the model to use nucleus sampling, trimming away the bottom 10% of the long tail of improbable words. We further constrain it by setting top K to 50. This creates a hard ceiling. The model will never consider the 51st most likely word, completely eliminating the risk of bizarre hallucinations.
While controlling randomness dictates the style of the output, controlling the length dictates the structure and the cost. In the Bedrock playgrounds, you have powerful tools to limit how much text the model produces. The most fundamental parameter is max tokens, or response length. Why is this parameter so critical? Because foundation models are designed to continue generating text until they naturally conclude an idea. If a chatty model decides to write a 5-page essay when you only wanted a 1-sentence summary, you are wasting massive amounts of compute time and paying for unnecessary output tokens. Amazed. Setting a hard max token limit acts as an absolute computational ceiling, forcing the model to halt generation regardless of where it is in its thought process. However, abruptly cutting off the model can result in incomplete sentences. This brings us to the elegant solution: stop sequences. Stop sequences allow you to define a specific string of characters, such as a closing XML tag or the word end. The moment the model generates that exact sequence, the inference process terminates instantly. Excitedly, by utilizing stop sequences, you can force the model to output data in strict JSON formats or specific bulleted lists, ensuring your application code can parse the response predictably without dealing with runaway generation trailing off into unwanted commentary. This execution loop governs length. The model generates tokens, continuously checking if a stop sequence is detected for a graceful termination. If not, it checks the max tokens limit to enforce a hard cutoff, preventing runaway compute costs.
The ultimate goal of experimenting in the text and chat interfaces is not just to play, but to build. The Bedrock Playground serves as your drafting board. You tweak the prompt structure, you dial in the exact temperature and top P, you define your stop sequences, and you validate the output using compare mode. Once you achieve the perfect response in the browser, how do you operationalize it? Amazon Bedrock makes this incredibly seamless. At the bottom of the Playground interface, there is a button to view API request. Amazed! Clicking this instantly generates the exact JSON payload required to replicate your exact Playground configuration programmatically. You can copy this JSON directly into your AWS Lambda function, your Python script, or your LangChain application, ensuring that your production environment behaves identically to your sandbox experiments. This bridges the gap between experimentation and deployment. The Playground is where you master the cognitive behavior of the model, and the API is where you integrate that intelligence into your enterprise workflows. Never stop experimenting. The landscape of generative AI changes rapidly, and constant iteration in the Playground is how you maintain a competitive edge. We invite learners to like, subscribe, and visit quicktechie.com for premium and for recently updated material as per latest syllabus and certification prep, Q&A banks, ebooks, audiobooks, full training, interview guides. On YouTube, it may not be your latest contents. The transition to production is flawless. We tweak variables in the Playground to achieve perfect output, view the underlying API request, export the precise JSON payload, and deploy it directly into our AWS Lambda production environment.